Okay, let's continue on with some more of these chapter 5 problems. Here's number 29. Firefighter weighs this many newtons, slides down a pole with an acceleration. What's the magnitude of the vertical force on the firefighter from the pole? So let's see, I feel like that's still not focused that well. There we go. So thing we should probably do here, maybe it's not necessary, but to draw a free body diagram. So there's the firefighter, there's gravity pulling down on him, and then there's the pole pushing on him as well. So maybe I want to write FP for the pole. So when the firefighter is grabbing onto the pole is reacting Newton's third law and pulling on the firefighter and pulling him up. These things are going to be not balanced with each other because there's an acceleration down. So after we draw a free body diagram, we do F net equals ma. The net force here, if we take down as positive, is going to be Fg minus Fp. That's equal to ma. And I think that we can do it from there. If the acceleration is down as positive here, then that's going to be a positive number here. Excuse me. And then that's going to be a negative number here, so we'll be able to figure out the direction. And then the vertical force on the firefighter from the pole and vertical force on the pole from the firefighter are going to be exactly equal to each other because of Newton's third law. So whatever the firefighter puts on the pole puts back on the firefighter. So there you go. Okay, let's see what's next. We have 31. Block is projected up a frictionless plane with an initial speed. The incline is 32 degrees. How far up the plane does the block go? So that one, draw a line here. We're going to need to draw a free body diagram for that one. So there's our dot for our free body diagram. And we have gravity going down, which I'll just label as Fg. We're always going to have a normal force, Fn, like that. And there's nothing else. It's frictionless, so there's no other forces here. And this one's not so hard to set up, but as with most of these problems, we're going to take this gravity and break it into components. So that's that. That's our angle. This is Fg cosine theta, and this is Fg sine theta. Fg cosine theta and Fn are going to balance each other out, so we don't really care about that one. The only force we really need to deal with is this Fg sine theta. Let's see, it still seems like it's too bright. Okay, there we go. So we just deal with this Fg sine theta, and that's going to cause the acceleration. So once we have this, we have A equals F net over m. In the x direction here is what we're talking about, just in the direction of going up and down the plane right there. So that is going to be this one here. And you know the mass, you can find the acceleration. Then you can do all sorts of things with distances. 1/2 at squared plus v0t. Keeping things positive in the right direction, so choose a direction to be positive. If down the ramp is positive and up the ramp is negative, then this initial speed right here potentially has to be negative if up the ramp is negative. So just keep track of your positives and negatives for that one. It's very important. Let's see, 33. Elevator cab and its load have a combined mass. Find the tension in the supporting cab when it's moving downward and when it's brought to rest with a constant acceleration. Okay, so free body diagram. We've got Fg going down. We've got a tension going up. Now, depending on the situation, one of these might be bigger or smaller, or they might be the same. And then we have the mass of 1,600 kilograms. So if it's moving downward at a speed of 12 meters per second, then that's a constant speed, which means that these two things have to be balanced. So for this first one, originally moving downward, okay, never mind, is brought to rest with a constant acceleration and a distance of 42 meters. Okay, so never mind that. So we have a distance of 42 meters and it's brought to rest. So we need to figure out and we have an initial velocity here. So we have to figure out the acceleration, and then we can figure out the net force here. So we're going to write F net equals ma, as we usually do to start these problems. I know that it's going downward, but it's going to slow down. So the net force has to be in the up direction, and I'm going to call that positive. So I'm going to write this as T minus Fg equals ma, or I can write T minus mass times gravity equals ma. And we're looking for the tension. In order to find that, we first have to find the acceleration, and I'll let you figure that out, but probably a good equation to work with is our good v squared is v0 squared plus 2a delta x, and you know the distance and you know the initial velocity and you're going to get the acceleration. Just be careful with your pluses and minuses here, right? So pick a direction as positive, which we did already, and make sure that this starts out as negative, and which way is your acceleration going to be, and so forth. So you can do that one. Moving right along, 34. Let's see, crate is pushed with a constant speed up a frictionless ramp by horizontal force, F. Okay, this is interesting. We need this diagram here. What's the magnitude of F and the force on the crate from the ramp? So force on the crate from the ramp is going to be the normal force on the crate from the ramp. So that's going to be the normal force. And what's F? So this is a pretty interesting problem. I think that the way that this one is done is a little bit not standard in terms of how you're going to set it up and what you're going to break down in terms of the vector components. So let's draw a free body diagram for this. Oh good, I've got some space right here. So I've got my body, I've got gravity going down, which I'll label as Fg. I've got, ooh, that was a terrible straight line. I've got my normal force, and then I've got this one going this way, which is just labeled as F, just like that. We're trying to find the magnitude of F. We do know that it's going at a constant speed, so in any direction we choose, the acceleration is going to be 0. And we know the mass, and we know the angle as well, is 30 degrees. I think that the way this problem works out is that ordinarily I would take gravity and I would break gravity down into components, but I think it's harder to do that because then you'll have to break this force vector also into components, say one going this way and one going that way. I don't think that's the best way to do it. If I remember how to do this problem, I think it's better to actually break down the normal force into components and keep our axes up and down and side to side. And how that's going to look is I'm going to take, I need to kind of get rid of where I wrote my Fn because it's on the wrong side here. So I'm going to write it over here. So I'm going to break this into components like this and like this. So there's my Fn in my y direction, and here's my Fn in my x direction. And then if I can figure out the angles right here, I think I'm going to do this right, I hope. If this is my angle of my ramp, I'm pretty sure that this is the same angle right there. I hope I didn't mess that up. So that means that this Fn in the y direction right here is going to be Fn times cosine theta, and this is Fn sine theta. And then I can just start to equate some things because I know the acceleration is 0, so now I know I can balance this force with this force, and then this force with this force, and I can figure it out from there. So maybe just write it out in this x direction, the side-to-side direction. I know that my Fn sine theta has to be equal to my F over here. I know the angle, but I don't know Fn. But in my y direction, I can figure out Fn because I can relate these two things together. Fn cosine theta equals Fg. So I can use this to figure out this, put it in there, and figure out that. And then I know the normal force, the force on the crate from the ramp is going to be the normal force. So that's a cool problem, just has you think in a different direction. So there you go. 43, this is the one with the chain. Okay, fine. So we got 5 links on the chain. It's lifted vertically. And let's see, constant acceleration. Okay, good. So I know the acceleration. Find the magnitude of the force on link 1 from link 2. So that right there. And then the force on link 2 from link 3 and so forth and so forth. So this is going to be pretty similar to that other problem we had with all the disks, where I'm going to start to combine some things together right here. Each has a mass of 0.1 kilograms, so that's nice to know. Each of the masses is 0.1 kilograms. So if I'm going to draw a free body diagram of this first link right there, so there's the link. I'm going to have force of gravity going down, and then maybe I'll write this as force of 2 on 1 or something like that. The force of link 2 on link 1 that's pulling it up right there. And those have to balance. Oh, no, they're not balanced. It has a constant acceleration up of 2.5 meters per second. Okay, so this force here has to be a little bit bigger if it's going to accelerate up. Okay, that just makes it a teeny bit harder, but we can deal with this. So what do? We write F net equals ma. My net force, let's have up as the positive direction. So I'm going to have F21 which is what I'm looking for, or 1 on 2, either way you want to put this, 2 on 1, minus Fg equals ma. And I know all of these things. This is m times g, or the mass of link 1 times g, and that's the mass of link 1 as well. So I know the acceleration, I know this, and I can solve for this one. If I'm finding this next part over here, the force on link 2 from link 3, so this one here, I'm going to combine both of these together down here. So that's the mass of both of them together. So this force of gravity on both of them together is going to be m1 plus m2 times g. And then here's the force of link 3 on link 2, and then I just set it up in the same way that I did it before. And then I can keep going for all of them. The force, this one's actually pretty easy to do. The force on the top link from the person lifting the chain, just going to stick them all together. And it's actually pretty easy too, because each of these are the same mass. So this could just be 2m1, and you can kind of use the same equation over here. Don't forget, though, that when you're writing this equation, so how it's going to work out, F net equals ma. This is going to be F32 minus this Fg equals, and I have to combine these masses together, m1 plus m2 times a. So don't forget to combine the masses together. So I'll let you figure that one out. 49. Let's see. Hang on one sec. I feel like my lights are about to turn off. Okay, so we have the block of mass m. Let's see. Yeah, I guess we'll keep going here for maybe one more, then we'll stop the video. Okay, good. Block of mass m is pulled by this horizontal force on a frictionless floor, so that's easy. What's the magnitude of the block's acceleration? Okay, so pretty easy. Just draw a free body diagram. There's my force of gravity. There's my normal force. And then here's my other force. I guess I'll call it T, since it's a rope. Sure, you could call it F or you could call it T, either way. You know it's going to be 12 newtons. 12 newtons. This one is going to be mg down here. Now the normal force is going to be interesting because in a lot of problems, normal force and gravity are going to counteract each other, but that's not going to be the case here because this tension actually has a component in the vertical direction. So the way we're going to start this problem is break the tension down into components like this and this. So this is going to, and this is our angle right there. So here's t in the x direction. Here's t in the y direction. That's going to be t sine theta. That's going to be t cosine theta. And then we just start to mix them, things equal to each other. Oh, we don't even really care. Do we care about the normal force? In a sense we do. What's its value? So A is what's the magnitude of the block's acceleration. Okay, that's actually pretty easy to do because this is the only thing that's accelerating the block. So if I'm going to write a F net equals ma problem in just the x direction right here, I just have this t cosine theta equals ma. And I know t and I know theta and I know the mass, so I can figure out what A is. The magnitude is slowly increased. What's its value just before the block is lifted completely off the floor? So when the block is lifted completely off the floor, that means my normal force is going to 0. So what I need to do is make my normal force 0, in which case this is going to completely balance out that. So for part B, I just need this to balance this out, and then I'll figure that one out. And then what's the magnitude of the block's acceleration before it's completely lifted off the floor? So then I just have to, this will actually take a little bit of work to figure this out. Once I figure out what t is, then I have to go back and put a different t in here, and then I can figure out what this acceleration is when the block gets completely lifted off the floor. So got a little bit of work to do for that one, but I think you can figure it out. So let's stop here, and I'll make one more video for the rest of the problems.